All right, welcome. Today, we are going to pull back the curtain on the world of Linux firewalls. But we're not just going to list off a bunch of boring rules. No. Instead, we're going to go on a journey. We're going to follow a single tiny network packet from the moment it hits your computer to its final destination. So let's dive right in. I mean, really think about it. You click a link, and like magic, a web page appears. But in that split second, a little packet of data goes on this wild, complex adventure. And it's all controlled by this powerful gatekeeper living deep inside your operating system. So before we can actually follow our packet, we've got to understand the terrain, the landscape it's traveling through. And that landscape is pretty much dominated by a framework called NetFilter, which is built right into the heart of the Linux kernel. The best way to think of NetFilter is like the fundamental plumbing for all network control in Linux. It isn't the firewall itself, it's the powerful engine that lets tools like IP tables even exist. It gives us a series of hooks, these little interception points, where we can make decisions about packets. Okay, so what does this engine actually do for us? Well, it provides the essential toolkit for any modern firewall. You've got your basic packet filtering, this simple choice to allow or block something. It handles network address translation, or NAT, which is absolutely crucial for routing on private networks. And most importantly, it does connection tracking, which, as you're about to see, is where the real magic happens. Okay, let's get into the journey itself. A lot of people think a packet just arrives and smacks into this one giant wall of rules. But the reality is actually way more elegant. The packet travels along a very specific path with very specific checkpoints. And these checkpoints have a name. They're called chains. Just imagine them like intersections on a highway. At every single intersection, the kernel hits the brakes, takes a look at the packet, and decides which way it's going to go next, all based on a set of traffic laws. NetFilter gives us 5 of these main intersections. Pre-routing, that's the very first stop for any packet coming in. Then there's input, and that's for packets that are meant for an application on this machine. Forward is for packets that are just passing through on their way to somewhere else. Output is for all the packets created right here on this computer. And finally, post-routing is the absolute last chance to do something to a packet before it zips off onto the network. And this is the key to understanding the whole thing. A packet doesn't just visit all 5 chains. Its path depends entirely on what it's trying to do. Let's look at the 2 most common scenarios, side by side. So first up, let's imagine a packet coming from the internet, heading for a web server running on this very machine. It shows up at the network card and bam, it hits the pre-routing chain. The kernel looks at it and says, hey, this is for us. So it sends it straight to the input chain. From there, it's finally handed off to the web server. Nice and simple, a 2-step journey. But now, what if this computer is acting as a router? Okay, the packet arrives and it still hits pre-routing first. That never changes. But this time, the kernel sees the destination is some other computer. So instead of going to input, it gets sent down the forward chain. After it passes all the rules there, it makes one last stop at post-routing right before it's sent out. See? 3 steps, a totally different path. So we know a packet stops at these checkpoints, the chains, but how are the decisions actually made? Well, this is where 2 more big concepts come into play: tables and targets. Think of tables like different rulebooks, each for a specific job. You don't have just one giant list of rules. The filter table, its whole job is just to decide allow or deny. The NAT table's job is to rewrite addresses. Each table is a specialist. Now this slide here is where it all really starts to click. It shows you how all these pieces fit together, because not every rule book is available at every intersection. For instance, you can only do network address translation, the NAT table, in the pre-routing, output, and post-routing chains. You just can't do it in the input chain. This whole structure provides a logical order and stops you from making rules that don't make any sense. So let's trace it. A packet arrives at a chain. The kernel grabs the right table, the right rulebook. It reads down the list of rules. If a rule matches the packet, that rule points to a target. And the target, that's the final verdict. It's the action that gets taken. It could be accept, drop, reject. You get the idea. And speaking of verdicts, this brings up a really crucial choice for any sysadmin. Should you drop a packet or reject it? Drop is like giving the sender the silent treatment. The packet just vanishes. The sender waits and eventually just times out. Reject, on the other hand, is a polite but very firm no. It actually sends back an error message.
Now, from a security standpoint, drop is usually what you want because you're not giving an attacker any information. They don't know if the port is closed or if you're just ignoring them. Okay, so we've covered the path and the decisions. But modern firewalls have this one last layer of intelligence. They can remember things. They don't just see individual packets anymore, they see the entire conversation. And this is called stateful inspection.
So, when the very first packet of a brand new conversation arrives, let's say it's your first request to a website, the firewall's connection tracking system looks at it and marks it with the state new. It sees this as the very beginning of a conversation.
Now, every single packet after that is a valid part of that same conversation. The web servers reply back to you, your next request on that page, all of those get marked as established. The firewall just knows this traffic belongs to a conversation it already said yes to. And then there's the related state. This one is for when an already established connection needs to open up a second, totally separate connection to get its job done. The classic example is old school FTP, where you have one connection for commands and then a whole new one opens up for the actual file transfer. The firewall is smart enough to know that this second connection is related to the first one. And here's the crucial point, the big takeaway. State tracking is unbelievably efficient. You can write one single rule that says, allow all established and related traffic. And that one rule automatically lets in all the return traffic for connections that started from inside your network, without you having to write dozens and dozens of specific rules for every single port. It's really the foundation of modern firewall security. And this slide, well, it brings it all home. A packet arrives, it navigates a very specific path through the chains. At each checkpoint, it's judged against the rules in specialized tables. When a rule matches, a target decides its fate, and watching over the whole process is state tracking, which understands the entire conversation, not just one lonely packet.
So there you have it. Now you see the real architecture, the checkpoints, the rulebooks, the final actions. You can see that a firewall isn't just some simple block list. It's a structured, logical process. You have the map of the packet's journey. So the only question left is, how are you going to use it to protect your network?